Welcome to the 41st and final topic in Richard James Mathematics Resources. This one is entitled Matrix of Transformation. Now, here's another application of matrices. 1. We have used matrices to solve simultaneous equations. 2. We have used matrices to find the inverse of some functions. And 3. Although we will not apply the principles when we get there, matrices can be used in solving some more advanced linear programming problems. Mathematicians are not usually too egotistical, so in the event that matrix or any other mathematical device is employed in particular situations, it is to make life simpler rather than showing off some technical skills. If one is asked to determine the vertices of the image of a quadrilateral whose vertices are given and are known, of course, under a particular transformation, by the time the axes are placed on the graph paper, another person will be able to supply the answer if matrices are employed. If the problem requires that the original quadrilateral be drawn, even avoiding constructs involved in creating the image will save a lot of time. Well, what is the use of carrying out the constructs if the transformation can be so easily obtained? The knowledge and understanding of symmetry and other important relationships between an object and its image that we need to have an appreciation of in other branches of geometry cannot be achieved unless we are intimate with the process. Now, our first matrix of transformation that we are going to be looking at is the one that has to do with translation. The matrix of a translation is a column vector that is added to each point to be transformed. Each point is written as a column matrix. Given a point and its image under a translation, we should be able to determine the matrix or the vector of translation. So given a point and its image, so we have the point A, which is 2, negative 5, and we have the image which is A prime, negative 4, 3. We are required to determine the vector that translates A to A prime. So find the vector V of translation that maps the point A to its image A prime. The matrix of translation is added to each point that is to be transformed. Therefore, adding the vector V to the point A will give the image A prime. So, our matrix of a translation is a column vector that is added to the point that we are going to be transforming. So A is the original, we add the vector V, and the result is A prime. So how do we find the vector V? Making the vector of translation V the subject of the formula, and of course remember we did an entire topic, transposition of formulae. Therefore, this simple transposition should be no problem whatsoever. Of course, we are making V the subject of the formula, and so A has to be transposed to the other side. So the vector of translation is equal to the image minus the original. Substituting the point A and A prime into the equation, this is what we'll have. Of course, V is equal to A prime minus A. That is what we have derived from the original situation that we have here that says the point is to be added to the vector in order that we might get the image A prime. So we are transposing this. So V is equal to A prime minus A, and that is what we are going to do right now. We have A prime right here and we have A right there. So we are going to have negative 4, 3 minus 2, negative 5. That's what we have. That's our vector. Then we simplify that and we have negative 4 minus 2 is equal to negative 6. And 3 minus negative 5 is equal to 8. So, therefore, to find the vector of translation, subtract the original point from the image. And that's what we have here. The vector is equal to, we subtract the original point from the image, or it is equal to the image minus the original. The resulting vector may be used to transform all other points under the same circumstances. Now, to determine the vector of translation, we may use the rectangular coordinate system. Say, for argument's sake, you have an object that is translated, and you need to know the vector of translation. Now, we are going to plot the point and its image. But under other circumstances, we may have been given the original point and the image. So that's a 2, negative 5, and a prime, negative 4, 3. So let us plot those points. No problem seeing 2, negative 5. Let's see what 2, negative 5 looks like. Remember, we go x first, 2, then negative 5. So 2, then 1, 2, 3, 4, 5. So we go 2, then 5 in the negative y direction, and that's our a. What about a prime? We have a negative 4, 1, 2, 3, 4. And then we have positive 3 in the y direction, 1, 2, 3. To determine the vector of translation, count the number of units moved in the x and y directions in order to get from a to a prime. So remember that a is translated to a prime, so we are going to count our movement in the x direction and then in the y direction and see what we end up with. So the number of units in the x direction, right, so we go 1. This is, of course, where we begin, so we cannot call that 1. That would be 0. So we start right here and we say 1, 2, 3, 4, 5, 6. And then we go up 1, 2, 3, 4, 5, 6, 7, 8. So number of units in the y direction, that's it. And that turns out to be 8. So of course, the vector of translation is v is equal to negative 6, 8. And we have it right there. You may use any method to find the vector. Choose the one that is more convenient to the current situation. So if the situation is that you have it on the rectangular coordinate system already, you could just do the steps that we have just done. If you have the coordinates and you are never required to put those points on the coordinate system, and you did not have a graph supplied to you, then you may take the other approach where you just say vector is equal to image minus the original. So we are going to be looking at other transformations because we did 4 of them, and we are going to see that the other transformation, the matrices of the other transformations are different. So all other matrices of transformation apart from translation, that is, are 2 by 2 matrices that are used to multiply each point that is to be transformed. So whereas we are doing translation, we add a vector to the point. In this section, we are going to multiply our point by a 2 by 2 matrix. The coordinate system to be used in this section to determine the matrix of transformation will not be placed on a grid. This is because the only points that we will consider or will employ are 1, 0, 0, negative 1, negative 1, 0, and 0, 1. Well, you imagine that we don't really need to put up an entire coordinate system for that, but we can put up some figment of it. So there we have a representation of our system with just each one of these points just 1 unit away from the origin, each one just a single unit away from the origin. So we don't need a sophisticated system for that. The points and their relative positions are shown in the diagram, of course. We have it right there, no problem whatsoever. To determine the matrix of transformation, take the 2 points 1, 0 and 0, 1 and write them as a column of a 2 by 2 matrix. So we are going to write the points 1, 0 and 0, 1, but we are going to write them as the column of a 2 by 2 matrix. So the first point 1, 0 becomes the first column, and of course the second point becomes the second column. And of course you will be familiar with this because we did matrices, and of course it's a matter of doing some transposing right there. The points in that form are subject to the transformation, and the results are written as the columns of a 2 by 2 matrix, and that matrix will become the matrix of transformation. And that of course might be a little abstract, but we are going to put it into reality and see what it means. Now our first task is to determine the matrix of our reflection in the x-axis, and the x-axis has equation y is equal to 0. Y is equal to 0. So what are we going to do? Of course, the x-axis is the mirror line, and we are going to highlight it there. That's our x-axis. That is our mirror line. Let us reflect the point 1, 0. How do we reflect the point 1, 0? Don't forget that the point 1, 0 is on the mirror line. Because of this, its image will have the same location of 1, 0. Go home, go to your mirror, put your finger on the mirror and see where the image of your finger will be. Of course, it's going to be located right at that same point. So 1, 0 has image 1, 0. So let us reflect the point 0, 1. Now, what is our information there? Do not forget that its image is located along a line that is perpendicular to the mirror line. Remember that? When we're doing reflection, we draw a line that is perpendicular to the mirror line that goes from the point to its image. So do not forget that the line that goes from the point to its image is perpendicular to the mirror line. And of course the mirror line in this case is the x-axis. And of course the point is required to be equal distance from the mirror line. So this point, the distance from the mirror line is from here to here. Of course, let's see what the information that we have right there. The y-axis is already perpendicular to the mirror line, so we don't have any problem getting a perpendicular there. The image of 0, 1 may be located along the y-axis at the same distance from the axis as 0, 1, but on the opposite side of the mirror line. So this is our mirror line. It is already perpendicular to the y-axis. Therefore, our image is going to be located along this line. And where is it going to be? The same distance as this point from the mirror line. So the image is going to be the point right down here, equal distance. So that is where our image is going to be, 0, -1. The matrix of the reflection is therefore, remember, although we have determined our matrix using vertical movements, say we have these points that are written as columns and the images are written as columns. When we are reading a matrix, we always read a matrix row by row. So this one is 1, 0, 0, negative 1. If you read it column by column, in this case, it would read the same way, but do not develop that bad habit. So let us continue with our matrices of transformation. And of course, our section is reflection. And we are asking now, determine the matrix of a reflection in the y-axis. And the equation of the y-axis is x is equal to 0. So the y-axis is the mirror line, and that is our mirror line right there. So let us reflect the point 1, 0. The x-axis is already perpendicular to the mirror line. The image of 1, 0 may be located along the y-axis at the same distance as 1, 0, but on the opposite side of the mirror line. So this is our mirror line. It is perpendicular to the axis, and we need to go right across there, right across, and the point that we have here is a distance of 1 unit from the origin. So the one that we have over here is 1 unit from the origin also. So let's see what its image is. No doubt, negative 1, 0. So let us reflect the point 0, 1. What will happen to 0, 1? Of course, it is on the mirror line. So the point 0, 1 is on the mirror line, which is the y-axis. Because of this, its image will have the same location of 0, 1. The matrix of a reflection in the y-axis, which is the equation of the y-axis is x is equal to 0, is negative 1, 0, 0, negative 1. And for the reflections, it does not matter the direction in which you read the matrix, it will always turn out to be the same. But for rotation, it is different. So do not develop the bad habit of reading a matrix column by column. Matrix are to be read row by row. Now our another assignment, determine the matrix of a reflection in the line y is equal to x. Do not forget anything that you have learned in the previous topics, like what the line y is equal to x looks like. There it is anyway, we are reminding you. Let us reflect the point 1, 0. That's our point 1, 0, and it's located right there. So let's see what happens. Remember that 1, 0 and its image must be located in such a way that the line joining both is perpendicular to the mirror line. Not to mention that they should be equal distance from the mirror line. So we are going to go in that direction. So we are going to go in a direction perpendicular to the mirror line, which is that direction. And of course, they are equal distance from the mirror line. So 1, 0 will be reflected to 0, 1. What about the other one? So let us reflect the point 0, 1 and see what happens. That's our point 0, 1. It follows that if 0, 1 is the image of 1, 0, then 1, 0 is the image of 0, 1. If it does not follow, as I suggested, then apply the basic principles of reflection, which is the line joining the point to its image should be perpendicular to the mirror line, and they should be equal distance from the mirror line, and that would have taken us to that point right there, 1, 0. The matrix is of a reflection in the line y is equal to x, and it is 0, 1, 1, 0. Reading horizontally, of course, row by row. We are still with reflection, and we have a final one. Determine the matrix of a reflection in the line y is equal to negative x. So you also need to remember what the line y is equal to negative x looks like. And of course, it is explained in detail in equation of a straight line. That is where it is located in Richard James Mathematics Resources, and it's in volume 2, functions 1. So let us reflect the point 1, 0. Remember that 1, 0 and its image must be located in such a way that the line joining both is perpendicular to the mirror line. So a line that goes like that, perpendicular to the mirror line, like that. So its image turns out to be 0, negative 1, or we may look at it right here, 0, negative 1. So let us reflect the point 0, 1 and see what happens. 0, 1 is this point right there, perpendicular to the mirror line and equal distance from the mirror line right there. So let the point 0, 1 move also in such a way that its trajectory is perpendicular to the mirror line, and the mirror line is y is equal to negative x. The matrix of a reflection in the line y is equal to x is negative 1, 0, 0, negative 1. Rotation. Determine the matrix of a rotation 90 degrees clockwise about the origin. 90 degrees rotations should not pose too much problem because the axes are already mutually perpendicular to each other. So we should have no problem whatsoever with our rotation, especially not with 90 degrees. So let us rotate the point 1, 0. That's our point. The 90 degrees of rotation is shown by the perpendicular indicator. It is the angle by which the point will be rotated. So this is our indicator, 90 degrees. So this is the angle of rotation. So we are going to go like that. Right there. Rotation. Right there. So the image of 1, 0 is 0, negative 1. So let us rotate the point 0, 1. That's our point 0, 1. And the perpendicular mark is indicating the angle of rotation. So this is the angle this way. Right there. And of course the image of 0, 1 is 1, 0. The matrix of a rotation 90 degrees clockwise about the origin is 0, 1, negative 1, 0. Determine the matrix of a rotation 90 degrees anticlockwise about the origin. So our movement this time is anticlockwise. So let us rotate the point 1, 0. The 90 degrees is shown by the perpendicular indicator. It is the angle by which the point will be rotated. So this is going to go in that direction this time. So that moves to 0, 1. Let us rotate the point 0, 1. That's the point 0, 1. It rotates to negative 1, 0. The perpendicular mark, of course, is indicating the angle of rotation right here. So it goes from here, there, as we have seen. The matrix of a rotation 90 degrees anti-clockwise about the origin is, read that horizontally, 0, negative 1, 1, 0. And of course, we are seeing at this point that it does matter the direction in which we read our matrix. Determine the matrix of a rotation 180 degrees about the origin. 180 degrees is an angle on a straight line. The images will therefore be located on the same axis on the opposite side of the origin, and that is very simple. Let us rotate the point 1, 0. And the point 1, 0 is going to be rotated all the way around to the other side because we have angle on a straight line, so no problem with that. The point will go to the opposite side of the origin. So there we have it. So let us rotate the point 0, 1. That will go all the way around to the other side. So that point will go to the opposite side of the origin, and that's 0, negative 1. The matrix of a rotation 180 degrees about the origin is negative 1, 0, 0, negative 1. It is not necessary to show the movements of the points in size transformation. Let us determine the matrix of a size transformation with scale factor k that is centered at the origin. What do we do with the scale factor in size transformation? Since we use it as a multiplier, we will multiply our matrix by the scale factor k. So our original matrix is comprised, of course, of the points 1, 0 and 0, 1 written as the columns of a 2 by 2 matrix. And k is multiplied by that. And of course, k is going to be multiplied by every single element of the matrix. As usual, do not forget matrix multiplication, specifically scalar multiplication of matrices. And that is your answer. So this is a matrix of a size transformation with scale factor k that is centered at the origin. Before deriving matrices of transformation, we said that they are 2 by 2 matrices that are to be used to multiply points that are to be transformed. So we are going to transform points by the use of matrices. So let us use the matrix of a rotation by 90 degrees clockwise about the origin to transform the quadrilateral with vertices A, 2, 3, B, negative 1, 5, C, negative 7, negative 8, and D, 4, negative 6. Take the matrix. The points are then written as the column of the other matrix. And D is right there. So those are all of your points, and they are written as columns of the matrix that we are going to multiply this matrix of transformation. As a matter of fact, we could multiply the points one by one, but that is going to be wasting a lot of time and space. So we will now find the images of the points by matrix multiplication. We will not take the normal route. We will find the images one at a time. So remember, when we were doing our matrix multiplication, we took this row and we multiply all the columns. This time we are not going to be doing that. This time we are going to multiply this row by this column. So the top with the first, and the result is going to go to the top. And of course in the first position there. So finding the sum of the products is very easy in the transformation because one of them is always equal to 0. So if we say 0 times 2, that is 0, and 1 times 3, that's 3. So one of these always, one of the product is always equal to 0. So we just write down the other one. So we are writing down the image of A prime, so we have 3 right there. And of course, instead of going to the other column, we choose to use this row to multiply that same column. That is so that we can find the images one at a time. Usually, if the first one is correctly found, we do not need to work out the others, as a simple pattern exists. So if this one is correctly worked out, we don't need to work out the others. There's a pattern that we can follow and use it to write down the others. Notice here that the numbers have exchanged places and the sign of the lower one has changed. So these numbers would have exchanged positions right here, and we have changed the sign of the one that goes to the bottom. And we're going to do the same thing for B. So we're going to change these around. So the -1 is going to go down and the 5 is going to go to the top. And then we are going to change the sign of the one that is at the bottom, which is -1. It is going to be changed to +1. So we have 5, 1. And of course here, the -8 is going to go to the top. The -7 is going to go to the bottom. And we are going to change the sign of the one that is at the bottom, which is -7. It is going to be changed to +7. So we're going to have -8, 7. And of course, the same thing is going to happen right here. Change these around. -6 goes to the top. 4 goes to the bottom. And the sign of the one that is at the bottom is going to change. So -4 is going to be at the bottom. Right. Students should be aware that each transformation has its own pattern. So do not bother to go and use this pattern for every single transformation. When you are doing your transformation, work one out and work out the pattern on your own and just use it to write down the images of the others. So for each transformation, determine the pattern and use it. In examinations, the coordinates of the images are usually required. Leaving the answers as they are may not result in maximum marks. Students are required to extract the coordinates of the image from the resulting matrix. So, when preparing the points for matrix multiplication, they were written as the columns of the matrix. We will extract the images from the resulting matrix by writing each column in coordinate form. So that's your first one, and it is A prime 3, -2. Then your second, B prime 5, 1. Your third, and it is C prime -8, 7. And there we have D prime -6, -4. Be reminded that for most questions, you have to read them carefully. The correct answers are the coordinates that should be extracted from the resulting matrix. Examiners are well aware that brilliant students are so instructed, they sometimes request the position vector of the point to ensure that students are not supplying the correct answer based on some preconceived notion. So, read the question carefully. Most times, it is the coordinates that are required, but I've seen in a few cases where the examiners have requested the position vector of the points also. Students are required to demonstrate a knowledge of what matrix will transform the image A prime to the original point A. Remember that A prime is found by multiplying the point A by the matrix. So let us call the matrix A. So A prime is actually equal to M multiplied by A, the matrix multiplied by the original point. We need to get rid of the matrix M from the right hand side, just like in any transposition. So we need to get rid of the M from the right hand side, because right here we need to know what matrix will result in the original point A. So we need to get rid of this M, or we need to transpose it to the other side. And since it's being multiplied, we need to divide. Well, we're not going to be dividing by M. We are multiplying matrices, so we will multiply by the inverse instead. So instead of dividing, we multiply by the inverse instead. On the right hand side, the product of the matrix and its inverse is equal to the identity. The identity multiplied by A will result in the matrix A. And of course, it is more appropriate to write the expression with A as the subject, which is on the left hand side. The matrix that will transform A prime to A is M inverse. And I don't think that this should be any surprise. Composition of transformations. Given that a point P is transformed by the matrix A followed by the matrix B, students are sometimes required to demonstrate a knowledge of what single matrix product will carry out the entire transformation. Let P be the result of transforming by A only. And here we have this expression telling us that P prime is equal to A, the matrix A, multiplied by the original point P. The point P prime is then transformed by the matrix B, and the result is P double prime. The matrix B is not going to be operating on the point P, but on the point P prime, and the result is P double prime. Of course, P prime is determined already to be A multiplied by P. So do not forget that P prime is AP. So P double prime is equal to B times A times P. Here we have P prime is written there as AP. So P double prime is equal to B times A times P. The resulting matrix is therefore BA. Notice then that we have the product BA right there. So instead of AB, the matrix that will carry out the entire process is BA. Always remember that the matrix product that is responsible for carrying out the transformation represented by transformation A followed by transformation B is BA and not AB.